Welcome again to my presentation called ret2spec. This work was done together with my supervisor, Christian Rosso, at Cispa University. And the main topic of this presentation is speculative execution, which is an optimization technique used in modern processors. And what it does is actually predict the instructions that will come up next and start executing it before it is actually needed. And probably all of you have heard about it after Spectre came up. And what the authors of Spectre showed that speculative execution can actually be abused to leak memories from the same process or even across different processes. And the basic example of Spectre 1 is actually quite simple. It consists of 2 lines of C code. And by looking at the code, we can see the 2 main components of this attack. First is speculative execution, and the second is cache side channel attacks. And speculative execution is used to trigger speculative execution into the second line of code and executing it even though the if condition is not set. And then cache side channel is used to leak the values that will be read from the memory. And there are also other similar papers that propose different extensions. However, all of them use jump instructions to reach speculation. In our work, we will look at another type of branch instructions, that is return instructions, and we see how it can also be used to reach similar goals. Okay, let's go over some details or background before I go into details, and I will start by how cache side channels work. And as you all know, caches are the small components that keep data closer to the core, so that next time they are accessed, it will be faster to fetch them from one of these levels. In modern processors, we have, for example, L1, L2, L3 caches. And how the work is the following. If, for example, we have process 1 that reads data at address A, on the first time the access is made, it cannot be found in caches. Therefore, it has to be fetched from memory. And on the way back, it will be also stored into the caches. This means that next time P1 accesses the same data, it will be way fast. For example, 4 cycles instead of few hundred. But the problem here is that caches are also shared across different processes. This means if we have now process 2 accessing the same data, L1 will forward the data happily to P2. This means that this process can now measure the time it takes to get the data, and will realize that some other process on the same core has accessed the same data recently. The same thing can happen across different cores. For example, if we have the third process, P3, on core 3, and it accesses the same data, the data can be fetched from a shared last level cache instead of going to the memory. Now, the second component of Spectre is speculative execution. And to understand how it works, we need to look at out of order execution first. If we look at the following C code, from software's perspective, we assume that instructions are executed one after another in sequential order. However, because in hardware we already have execution units for all these different type of instructions, it is a waste of resources to execute them sequentially. Instead, out of order execution wants to schedule them based on their data dependency and not based on their program order. But the problem still is that we need to retire the instructions in program orders. This means we need to update the architectural state in the order it is written in the program. And to solve this issue, the pipeline is split into 2 stages, execution and the write-back stages. Execution stage simply does all the computations. This includes memory accesses. And write-back stage updates the architectural state. This means writes the result to the registers or to the memory. And now, having this separation, instructions can be scheduled at the same time, execution stages, while write-back stages are committed in the program order. Now, this brings us to speculative execution, and to see why it's important, let's look at the following C code. Let's assume that we have this if instruction at the beginning, and after the condition, before the condition is evaluated, we do not know which path is taken, if body or else body. This means we have to wait until it's evaluated, and only after that we can schedule the remaining instructions. And again, this means that at every branch instruction we have to wait until condition is evaluated, and we are losing the utilization of hardware. So instead, what branch predictor does is it will predict the possible outcome of if condition For example, if we have now that if body will be executed, now we know the actual path that needs to be executed, and we schedule it together in parallel, and we start speculative execution. And at some point, we reach a state where we have finished evaluating the if condition. And at this point, we know if our initial prediction was correct or not. If it was correct, this means we have executed the correct set of instructions. We write the results back to architectural state, and we are done. However, if the execution or prediction was wrong, this means that we have executed instructions from the wrong path, and this means we cannot update the architectural state. But this can be simply done by flushing the write-back pipeline stages for these instructions, and instead scheduling the ones that we needed to execute. And note that this also includes a final XOR instruction, which now has to get the correct data from previous execution. And the important aspect here is that although we didn't write back the result back to architectural state, we still executed the instructions on the wrong path. And these instructions might have some side effect on architecture. For example, second instruction is a memory access, which would trigger caching some of the data. Now, knowing how speculative execution works, one of the core components there is branch predictor. And branch predictor or type of branch predictor depends on type of branch instruction. And in the previous research, we have seen conditional jumps and indirect jumps and calls that have been used. In our work, we will instead concentrate on return instructions. So let's see how return instructions are predicted in modern hardware. So basically, when we do call instruction, at that point, we know the return address. This means that we need to store this return addresses somewhere in microarchitectural buffer. And return stack buffer is one type of buffer that is used in modern hardware. How it works is the following. Every time you execute call instruction, you push a return address on this buffer. And then every time you execute return instruction, you pop a top entry from there and you use it for prediction. But there is a clear problem here because the RSP has fixed size. And what happens when we have an underflow? And there are three possible cases that we are aware of. First is to simply stop prediction. This is not really efficient. Second is to use RSP as cyclic buffer and keep predicting same entries over and over again. This can help, for example, if there are if we have deep recursive functions. And finally, we can also use branch target buffers like indirect jump predictors to predict return addresses. And this last technique is used in recent architectures after Skylake in Intel. So knowing how this works now, let's see how we can trigger misprediction. And the basic idea that we want to do here is we have stack, which contains real return addresses, and we have RSP, which contains predicted return addresses. This means whenever they have mismatch, next time we return, we will speculate the return address with the entry in RSP, but the real address is in stack, so we have a mismatch. And there are some other ways to do it, but in our work, we will concentrate on context switches and cyclic RSP underflows. So this brings us to our first attack that will use context switches to trigger RSP, to trigger return address misprediction, and we see how we can use it. And on a higher level, the general idea that we are using here is the following. Let's assume we have process 1 running on the core, and it is doing some execution and also doing some system function calls and creating some entries on return stack buffer. And now at some point, operating system will decide that it's time to context switch from process 1 to process 2. And context switch also includes changing the stack of the execution program. And this means stack is changed, but however, the RSP remains the same that was in P1. And now when process 2 continues execution, if it now executes return instructions, this means the entries that will be used for prediction will be taken from P1. And this is a clear problem if we assume now that P1 is controlled by the attacker and P2 is a victim process. This means that the attacker process will be able to inject arbitrary values in RSP entries that will later be used in the victim. And we use this technique to create our proof of concept for this. In this, we assume that victim process is a command line program that constantly waits for an input from operating system. So it runs in an infinite loop, tries to get a new character, for example, that was typed on the keyboard. So it will execute a few function calls, then system call to go to kernel, and then kernel will check if there is a new input available. But because users typically cannot type that fast, there won't be always new input. This means that operating system has now to put victim process to sleep and instead schedule some other processes. And now some other process is the attacker process that we assume. And the attacker process does a simple set of execution. What it does is it fills RSP entries with the addresses of gadgets. This can be done by executing call instructions in a controlled manner. And then it will yield the execution. And yielding the execution means that it will ask operating system to schedule next process. But now we know that we assume that there are only attacker and the victim process running on the same core. This means, and we also know that victim cannot run because it is waiting for an input which is not there yet. This means attacker process will run over and over again until at some point user presses a key and new input is available. And what happens then is that next time attacker process yields the execution, the victim process will be run. And here we know that because victim process in the last time stopped inside the kernel, it will execute at least few or couple of function returns. And these two returns in this case, for example, will use entries that were put there by the attacker. So now we are given that attacker can inject arbitrary entries into victim process, and victim process will use this at least two entries to speculatively execute attacker-controlled position. So now we want to see what type of gadget do we want to execute. And our final goal is to leak the keys as they are being typed by the user. And to see what gadget will look like, we need to look at the execution context right before return instruction is executed. This is the context that will be used in speculative execution. And looking at that, we see that RAX will contain the input character that was returned by the operating system, and R10 will point somewhere inside libc. And why it is important is that libc is a shared memory between attacker and the victim. And this means that if victim touches any of the cache lines inside libc, then attacker can use cache sidechain attack to measure that. So one of the possible gadgets that can be useful here is the following two instructions. Shifting RAX, for example, by 8. This can be also some other values. We need that to align input character at least at cache line. And then we use another memory operation which uses this value and accesses memory from the base address R10. So somewhere inside libc. So the entire execution will look like that. For example, let's assume that while victim was sleeping and attacker was executing, user pressed capital K, and then victim started executing and it speculatively executed the gadget that was controlled by the attacker. This means that libc at offset hex 4B00, which is a K shifted to the left by 8, will be accessed. And now we have another process running on a sibling hyperthread next to victim and attacker, and it will go over all the cache lines in libc and check which of the cache lines have been actually cached. And the ones that was cached will correspond to the input character that we want to leak. Now, this brings us to possible countermeasures against this attack. And as we see, that main problem is that when we do context switch, we change stack, but RSP remains the same. We also want to get rid of attacker entries from RSP. And there is no direct instructions that can be used here. However, operating system can still do chain of call instructions. And by doing that, they will effectively remove all attacker-controlled entries from RSP. And this should be done, for example, at every context switch. And this solution was also proposed by Intel and was used also in Linux. However, it was not applied to all architectures. And we show that it needs to be applied to all architectures to protect user-to-user attacks. Now, let's consider our second attack. In this case, we assume that attacker is in control of some scripting language like JavaScript or WebAssembly inside browser. And also the victim is running CPU which has cyclic RSP entries. And our attacker wants to use cyclic RSPs to trigger misprediction and then use misprediction to leak arbitrary memory from arbitrary addresses. So let's see how we can reach RSP misprediction from cyclic RSPs. So if we assume that we have the following stack and RSP, and we have functions A and B, if we call function A recursively n times, and then we call function B recursively 4 times, here we assume that 4 is the size of RSP. This means that we put on in RSP now we have only B's as address predictions. And now if we return 4 times from function B, the real pointer will be pointed by stack will be pointing to function A. However, the RSP will contain B's as their predicted addresses. This means that now the following n return instructions will all predict the return address to be in B and start speculatively execute the code here. However, the real return address is in function A, and also all the registers are set according to function A, and also the stack frame is pointed there. So with this in mind, we created the following 2 functions in WebAssembly. We have function A and function B, and we use the previous technique to do the following execution. We call A recursively n times, then we switch to B, and also execute B recursively 16 times. Now here we use recursive call 16 times because most common size of RSPs are 16 in modern CPUs. So we created all B's inside RSP, and now we return 16 times to change control flow from B to A. So what happens now is that every next n execution of return instruction will return value address, which is a long integer. However, function B actually expects the return value to be character pointer. This means if we look at the disassembly, the attacker can now control 64-bit values that will be put into RAX. And now we have memory access that will use this RAX as an offset. And putting these 2 together will allow us to do the following execution. We can read the initial byte. This will be from the beginning of WebAssembly heap, but arbitrary 64 bits. This means we can effectively read the entire address space. Then we can do arbitrary memory operation or arithmetic or shift operation. In our case, we will shift this value by 12 on the left. So this is done to align it to page size. And finally, we will do another memory access from base address of WebAssembly heap and using the value that we have just leaked. And what it will do is, if the leaked value was 1, it will cache the second page of the WebAssembly heap. And what we need to do is just go over all of the heap pages of WebAssembly, and the ones that was cached will correspond to the leaked value. So again, we go back to countermeasures for our second attack now. And the countermeasures here are similar to what was proposed for Spectre variant 1. For example, adding speculative barriers, which is, for example, L-fence, every time we expect speculation. In our case, it will be instructions following call. Another way to avoid this is to use ret polines. In our case, we have to change ret polines so that now they also work for return instructions. Before they were proposed for indirect jumps. And finally, because this attack is browser specific, browser vendors decided to go with strict site isolation to remove all possible sensitive data from their sandbox and also renderer process. And this means that even if attacker now has arbitrary memory read, nothing can be leaked that is important. This concludes my talk. In our presentation, we showed that return instructions can be used also to trigger speculative execution, and we demonstrated how this can be used to leak information across processes, and also showed that cyclic RSPs can be used to trigger mispeculation in JavaScript that can lead to arbitrary memory address leaks. So thank you for listening. I will take your questions now.
Hi, John Crizzle, University of Rochester. I'm a bit confused by your proposed countermeasures. I would tend to think that load fences would not stop the predictive aspect of the attack, where you're trying to, where the processor just figures out where it's supposed to fetch instructions next. And then ret-polyne, since you're actually poisoning the return stack buffer, the ret-polyne is using that in order to stay in this loop, right? Until it actually knows where it's supposed to jump to. So I don't see how either of these defenses would actually be an effective countermeasure against your attack.
So first, L-fences in controlled, in WebAssembly generated code, for example. We know that we can only speculatively execute code that is after call. This means when this will be predicted after cyclic buffer injection, we will start executing L-fence, and L-fence will not allow continuation of speculative execution.
Right, but you still have poisoning the return stack buffer, correct?
Yeah, but if you cannot use it, loses its meaning, right?
All right, I think maybe we should talk offline about it.
And for
ret-polynes?
Yeah, for the second one, what ret-polynes do is, instead of doing return instructions, you will have this sequence of instructions. And when you execute first call instruction, you will add one more predicted return address on top of RSP. And then when you do return, that address will be used for speculation. However, you also in the middle change the stack. So real return address will be pointing to the original return address, while speculatively you go to the speculate label that you see here. And there you basically have infinite loop, and you are trapping speculative execution inside this tight loop.
But what happens if there's an interrupt during that loop?
So you go to kernel.
Right, you go to kernel, and then you run your attacker process, and they poison the RSP.
You mean if this is effective against cross-process attack?
Well, the attack that you've proposed.
In our second attack, this is effective.
Okay, we need to chat offline, because okay. this makes no sense to me at all.
Okay.
Any other questions? Let's thank Georgia again.